Okay, so my name is Matias Jaskari, and I am from the University of Oulu, the same FMT research group that Antti is from this presentation before. And yeah, the topic of this short presentation is about how we can enhance the fatigue behavior of powder bed fusion Inconel just through surface quality optimization. So very straightforward presentation of engineering ways of introduction, fabrication, experimental, and so on. So as you most probably know, Inconel is often used in demanding applications because of its high strength and desirable properties, especially in high temperature applications. And the powder bed fusion itself, the process itself, enables us to use more freedom in part design and in the fabrication itself. And this is good, especially for Inconel, because Inconel is known it's very difficult to machine because of the hardness and so on. So additive manufacturing gives us more freedom, and it is printable material. And well, Inconel is expensive, and the powder bed fusion process itself, the fabrication is relatively expensive. And I see it also that this actually mitigates the material cost. So even though the Inconel is expensive, but the powder bed fusion is also, so we can produce specialized parts for specialized needs. But then we have this other issue that or quite often the quality that we can get through the powder bed fusion, it can be quite poor. And the fabricated materials are known to be prone, especially for the defect-driven failures in dynamic loading. There are, for example, some papers that dictate that there are over 100 process parameters that dictate the outcome of the fabrication itself. So we can consider this kind of levels of AM quality triangle here, and in the lowest part we have the lowest quality. So we can start that first. We need only a part that needs to be made out of metal, and if we increase the quality, then we need to meet the dataset values, and then when we have critical loads, the fatigue becomes critical, and so if we go higher, we need certification, and then we have the extremely critical components that are, for example, for aerospace and nuclear industries. But then usual needs are, industrial needs are the lower three ones. But the idea is that how can we get to the top ones? And for this, we applied for this national funded project streams. And like Antti said, that very fatigued and tested more than 10,000 samples in total to get this benchmarking and database for this kind of data. So what we did in this study is that we fabricated this kind of a standardized platform. We printed basically samples in vertical and diagonal orientation, and we have bending fatigue, we have axial fatigue, tensile samples, and impact toughness samples, also some powder samples, but in this study we used only the vertical ones. For the fabrication, we have an SLM printer ourselves in our campus, but this one was printed by using this EOS M290 system, and it is a closed machine, so we cannot really fiddle with it. We just press play, basically, and so these commercial 40-micron printing parameters were used. And to make things clear as possible, we used unused powder with a granular size of 14 to 45 microns. And of course, the printing was done in argon atmosphere. After the printing, the samples went through the conventional solution annealing first in 960 degrees for 2 hours, and then double aging for 8 hours, first in 720 and then in 620 degrees. And then after this, and removing the samples from the platform, part of the samples we then electropolished using this commercial D-light equipment, and we could decrease the roughness value, surface roughness value, from 10 microns to less than 1 micron. So we could really test the effect of the material itself and not just the surface. So the testing was done in uniaxial way, so fatigue and tensile. And the samples were designed so that we can test them in as-built condition if we want. So we don't need to do any prior machining. So we have these tensile and fatigue and microstructure samples. First, the tensile tests were done in according, of course, the ISO standard. We use round samples with a nice diameter and test length, so we don't have that increased necking effect. For the fatigue, we used the load-controlled axial testing with stress ratio of R-1 and with the cutoff cycle limit of 2 million cycles. And this is partly due of the high amount of the samples we did in the project. Usually we fatigue up to 10 million cycles because our equipment allows us to use the testing frequencies up to 100 Hertz. But the focus in this study is in the high cycle regime. And at this stage, 12 samples per case were studied. And for the fatigue, we use round samples with quite high diameter of 60 millimeters and length of 12. So we have quite nice test volume. So about the material itself. So if we look at the static properties here, we can see that there is a clear anisotropy between the testing directions. Strength is lower in this vertical direction that we studied in the fatigue, but the elongations are higher, and this agrees with the literature. If you check the microstructure, so after printing and heat treatment, we still have this typical dendritic austenitic or FCC structure. So this one is the building direction is upwards, and this is X. So you can see that there is maybe some columnarity, so meaning that the heat input is relatively high. And when we look from the other direction in XY, you can see it is more uneven, or maybe even that the columnarity is gone, of course, and you can see some finer grain growth in between the laser hatching tracks. So the fatigue itself. By just electropolishing the samples, we can immediately see that we increase the fatigue behavior, and the FAT, the fatigue limit, 50% probability limit increased over 90%. So from 220 megapascals to 420. And the treatment seems to be beneficial for the whole high cycle fatigue regime. But still the ratio of this FAT versus the tensile strength ratio is quite low. It's lower than the ideal of 0.5 from the tensile strength, but it is still higher than the 0.16 of the as-built ones. The results that we obtained here, they correspond relatively well to the values obtained in the literature. So there are a couple of papers, for example, and for the polished or machined condition with smooth surface, they get roughly the 400 to 500 megapascals with this kind of heat treatment. This is perhaps a slightly lower value for the as-built one, but this is always dependent on the machine itself. So you might have slightly rougher surface, or you have the downskin effect, or whatever there is that can lower this value or change it. So the deviation is usually higher in this one. Yes, and in our case, we could see from the fracture surface that we studied that we were able to print quite dense material because all of the initiations were from the surface, regardless of this surface condition. So of course the as-built structures, they fractured from the surface, but also these electropolished ones. And the crack propagation seems to be quite cleavage type in the beginning before the propagation rates. Of course, this smoother surface caused lower stress concentrations for the geometry factor, and that led to higher lifetimes. So outlook and what we will continue doing. So the present studies show that the surface roughness has a considerable effect, also with the Inconel, of course, of this high hardness. But more detailed analysis is needed to verify the effect of the residual stresses that are usually present in AM materials and what are the effect of the secondary phases in the crack initiations. So we know that we have an elemental segregation and we have the secondary phases like gamma double prime and so on. So what are the effect in here? But then we can also think further that instead of this electropolishing, of course, it is a nice way to produce parts, but it is also prone to deviation and so on. So, for example, surface attrition treatments such as severe shot peening, that how could they affect in these kind of hard but relatively ductile materials? And this usually cause you beneficial these stress fields on the surface so that you move the actual crack initiation to the inside of the sample, and this usually is seen in a high increase in the fatigue resistance. But thank you.